Ladies and gentlemen, welcome to another episode of Science Without Consensus, exclusively on Rumble, 8 p.m. Mountain Time, Saturday night. Tonight, we're going to be talking about a topic that's been in the news. The South Atlantic Anomaly is growing, and it's growing rapidly. We'll discuss what that means, what it is or is not, and the implications it may have with our weakening magnetic field. I'm your host, Diamond, from the Oppenheimer Ranch Project, and joining me is my lovely partner and co-host, Leah Shaper.
Hello.
Welcome to the show. We didn't have us blown up here like in the beginning.
Yeah, you screwed it up.
Oh, my God. All right. Well, we're going to be talking about the South Atlantic Anomaly, what it may be, why it is where it is, and what is in the news. Yeah. So do you have anything you want to say before we dive in?
No, let's just jump into it.
Okay, there it is. That is the South Atlantic Anomaly. Here's the United States. Here's South America. Here's the Atlantic. And the dark region here is representing weaker magnetic field than the rest. So the orange areas would be a high magnetic field. And the highest field strength here in this picture would be just south of Australia, in this zone. And this would be the weakest field strength.
Mm-hmm.
Now, these are not related to the current pole positions.
No.
The high field strength is. That is where the current South Pole is, somewhere just offshore here off of Antarctica. But the North Pole is up here north of Siberia, where this other high field strength is. Isn't that interesting?
Well, and that's the thing, right? You have to make the distinction that the polarity is a different thing than the field intensity.
Yeah.
Right. And so the poles would indicate the polarity, whereas the field intensity is a measure of strength.
Yeah. So the South Atlantic Anomaly is an area on Earth's inner Van Allen radiation belt, comes closest to Earth's surface. That's a lot to say there. Let's open up this. Okay, bear with me. Here we are. So here is the rotational axis of Earth. Can you see this?
Mm-hmm.
Okay. That way I don't have to go check. These field lines in the gray and red are magnetic field lines, and we are a magnet. Earth is a magnet. It has a north and a south polarity, and it has magnetic field lines that wrap around from north to south. That makes sense, correct?
Mm-hmm.
But it's slightly tilted here. You can see it, right?
Mm-hmm.
The magnetic pole is slightly tilted, and therefore those field lines are tilted. And the Van Allen radiation belts are the red ones here.
Mm-hmm.
And they're pointing an arrow where the South Atlantic Anomaly is. And it corresponds to where that radiation belt enters the Earth.
Right.
My question is, how come we don't have 4 anomalies at all these entries?
That was exactly my question, right? So numerous people have pointed out, right, like you just said, the proximity of the Van Allen belts to this particular spot, but obviously the Van Allen belts are close to Earth in other areas as well. So why do we not have other such anomalies?
That is a good question.
Yeah.
But satellite data from the swarm satellites reveal that the weak region in Earth's magnetic field at this spot, let's go back, has grown by an area roughly half the size of continental Europe in the last 10 years. Now that, to me, sounds significant.
Mm-hmm.
What are your thoughts?
Well, just for context, I think it's useful to note that where the magnetic field is generally at its weakest, which is equatorial, you would usually find strengths around 2,500 nanoteslas, somewhere around there. At the poles, it would be about 65,000. Did I say 25,000 earlier?
25,000. Yeah.
So equatorially, it would be about 25,000 nanoteslas, and at the poles, roughly 65,000 nanoteslas. This weak area, the South American anomaly, is about in the realm of 22,000 nanoteslas, close to 22,000 nanoteslas currently.
Yeah.
And that's down about roughly 400 nanoteslas from 11 years ago. And then at the poles, I'm sorry, not at the poles, but at the strong areas, the yellow and orange areas, the yellow being the largest, is currently about 61,000. I'll just give you the exact figure, 61,619 nanoteslas. So, that just gives you some context for how weak areas are and how strong areas are.
Yeah, and this graphic, you kind of
Yeah.
can get some idea in the amount of change.
Yeah. Yeah.
And also here in this graph, 2014 up top, 2025 on the bottom, you can see that the purple area has grown significantly.
Right. Yeah. I mean, I
And
think that
you can even see some of the high field strength areas increasing in this time period as well.
Right. So the area over that's sort of above North America, that strong area has weakened in the last 11 years. But the area over Siberia has gotten stronger, as has the area near Australia. So, I mean, I think that knowing the scale is sort of important for understanding that actually this magnetic field seems like a kind of a delicate system, you
Yeah.
know?
In fact, we're going to get to some graphs where if you look at different scales, like we've got that paper on the pre-pottery Neolithic and the pottery period, you look at a very small time frame, a few thousand years, and the field is changing. It's highly variable.
Yeah, I mean it is, but like what I'm saying is like significant differences, like numerically, don't actually appear to be that significant. So for the South American anomaly, right, it dropped from 22,430 nanoteslas to 22,000 excuse me, I can't talk today, 22,094 nanoteslas. So it only dropped by 400 nanoteslas, but that drop in the overall system is actually quite significant. So
Right.
that's why I'm saying it's kind of a delicate system.
Right. And on this graph, it would only be a tiny piece of this graph.
Right.
So just down here in this bottom corner.
Yeah.
So this little portion would be that 400 nanotesla. But look at the decline since 1850.
Right.
That is pretty significant. It leveled off here 1900 to 1950, but it's rapidly declining.
Right.
The South Atlantic anomaly.
Right.
Now, does that have some connection with our weakening magnetic field?
Right.
That's the question.
Right. So, I mean, there's a few things in here I think that you have to consider in that respect. One, and this is something I didn't exactly realize until today, the South American anomaly is not new by any stretch of the imagination. So we have another paper showing that the South American anomaly has been around for at least 11 million years. So what it designates is it's a regular area of magnetic instability, right? So it's like it's stable in the sense that it's been there a very long time, but it is an unstable region. So it's a stable instability, if that makes sense. But then you also have to consider that this anomaly, that area has grown, and its strength has decreased. So it's not the existence of the South American anomaly that points towards a reversal, but rather its changes, its growth in size and its weakening intensity.
Yeah, I think that there is a direct correlation between the growth and shrinkage of this area and what's going on with the magnetic field on Earth.
Yeah.
Now, because it's been around for millions of years, and because we've had complete polarity shifts, we've had magnetic excursions, all kind of stuff, it probably has nothing to do directly with the magnetic field. It's just a feature that is. And they initially explain how the magnetic field is formed by the liquid inner and outer core nonsense. But what we now know is that inside the Earth, there's these low velocity shear zones and provinces that we didn't know about before. And they correspond to areas of volcanism like the East African Rift Zone and the South Atlantic anomaly. So it's the composition of Earth plus the magnetic field that probably causes this.
Right.
And it's been there for a very long time because the inner three-dimensional workings of Earth don't change much in 11 million years. That's a blip, in our geologic time frame.
Yeah. Yeah.
It seems like major changes occur every 100 million or more at those mass extinction boundaries where there's complete reworking of everything on Earth. We often have huge volcanic events, the largest ever known, like the Deccan traps, the Siberian traps, etc. And it's all because of this internal three-dimensional structure of Earth that we really just learned about and we know nothing about.
Right.
And then you throw in expanding Earth, and God knows where it gets us. We know nothing about nothing.
Very, very, very little. I will say though that looking at this three-dimensional structure inside Earth and how that relates to the position of the South American anomaly plus the Van Allen belt contact, that probably explains why we only have this one anomaly instead of 4, right? It's dependent on the internal structure of Earth and how that interacts with the Van Allen belts.
Yeah, and with the 11 million year paper, let's pull that back up. I've got
Which is a great paper, by the way.
So many tabs.
Right.
So on this paper, they're using...
Do you have the actual paper? There's a link for it in this article.
Yeah. Elevated paleomagnetic dispersion at St. Helena suggests long-lived anomalous behavior. Now, the problem with the paper is that they're using volcanic eruptions that are the closest they are is 100,000 years apart. They typically are 1 million years apart. So it's not giving you very high resolution information. It's just telling you that this weak area was here during these eruptions. They don't really, you know what I'm saying?
Yeah, and in reality, the data set that they're using ranges from 8.8 million years ago to 10.3 million years ago.
Yeah.
So, I mean, you could argue maybe that the anomaly was there, let's say 10 million years ago, and went away and came back. You could maybe make that argument, right? To my reading of this, that seems unlikely. It seems more likely that it's been there a long time. But it's certainly, I think you can say that the status of the South American anomaly is a symptom of where we're at in terms of our overall field strength and whether or not we're headed into an excursion or a reversal.
Right. And if this is geomorphic, it's because of the Earth's inner construction. It's may have been there as long as Earth's inner construction has been like it is. So for tens of millions of years, and it just changes in size and strength. That's it.
Right.
And it probably changes in size and strength directly related to the field strength.
Yeah. Which, I mean, it makes sense because...
And here's another one. Here's another piece. It doesn't matter what the polarity of Earth is, because we've switched polarity several times in 11 million years, and it doesn't move.
That part I find especially interesting, right? Like when I was first looking at this paper, I was really scratching my head because I was not expecting an anomaly like this to be able to persist through that kind of dynamic, where our polarity has flipped and changed. But really, that polarity flipping, it's just a summation of all of the polarized areas on Earth and how they come out at the end of the day. Does that make sense? I don't know if I'm not saying that right. Like you're adding up all of the positive areas and where they are geographically. Let me think about how to say that. Let's move on.
Here's a pretty picture. And so that star there, that's the location of St. Helena, in case you're wondering, which is kind of in the middle of the Atlantic here.
Yeah, that's where they took all the measurements to determine that this thing was around 10 million years ago.
And you can see this is the paleo location of St. Helena. And you can see how much movement has occurred due to the mid-ocean ridge
Yeah.
That's a lot of, and
That's
that's only
fascinating.
in 11 million years. That's a lot
Right.
of movement.
Yeah.
But you have to consider that the Atlantic is new. There was no Atlantic 180 million years ago. There was just a crack.
Mm-hmm.
So it's a new ocean.
Mm-hmm. Mm-hmm.
And that's kind
You
of interesting.
know, I did for a minute wonder about the relationship of the South American anomaly, considering that it's moved more into Southern Africa. And then that started making me think about the East African rift zone and wondering if there's a relationship to the expansion happening there.
Yeah, could be. Let's take a look at this paper. Rapid changes in strength and direction of Earth's magnetic field over the past 100,000 years. Did I send you that?
Yep.
Oh, I just erased something.
Uh-oh.
So just for background, this is so the VADM is a measure of the magnetic field strength of Earth. And you can see here, take a look at this. 8,000 to 5,000 years ago, we had a dip here, a significant dip, just like we're dipping into today.
Mm-hmm.
That's kind of interesting.
Mm-hmm.
And we've often said that, you know, these weak field times is when we get bombarded by cosmic rays. And there's lots of significant stuff happening 9,000 years ago to about 5,000 years ago.
Mm-hmm.
You know, all the major civilizations are developing, and maybe it has something to do with this cosmic ray bombardment.
Right. The same way that, we talk about KP0, right, which is when we'd be getting on sort of a more daily scale when we'd get the most cosmic bombardment.
Yeah.
And we talk about, people having heightened psychic abilities during KP0, etc.
Yes, I'm looking for a
So,
graph.
so maybe there's a connection between, obviously cosmic bombardment, doesn't it, we don't fare quite as well in a physical sense, right? We'd be more subject to gene mutations and extinctions and biological problems, but at the same time it seems to impact our brains in a positive way, which is interesting.
Yeah, now here's the last 800,000 years, and this goes all the way back to the last polarity change, which is the Brunus Matuyama right here, 780,000 years ago. The polarity of Earth changed north to south, south to north.
Mm-hmm.
And the South Atlantic anomaly was still there.
Right.
Yeah. But you can see the field strength in the last 800,000 years is very highly variable with no specificity. And we pointed this out time and time again, that there's no 12,000 or 26,000 year cycle here.
No, which is pretty interesting considering that the sun's magnetic reversals are on a very regular schedule.
Yeah.
So I was thinking about that today and I was like, okay, is that a reflection of the difference between what is going on internally inside the sun versus what's going on internally in the earth? I don't know the answer to that. It's just something I'm chewing on, but it's a really interesting question. You would think, given that obviously our magnetic field having a relationship to the magnetic field of the sun, you would kind of think that they would both be on a regular schedule, but that's clearly not the case from the data that we have.
Yeah, I think that the graph that you're looking at here has everything to do with the sun, in the sense that you see these sections that are like, there's lots of little lines up and down here.
Yeah.
So maybe the 11-year, well, it's actually a 22-year hail cycle. The 11-year solar cycle is only half of the reversal.
Mm-hmm.
It's only north-south, so that's only half. It takes 22 years for the full reversal.
Mm-hmm.
That I think the amplitude of that change in Earth's magnetic field is small. And it's what we're looking at here, these little tiny up and downs.
Mm-hmm. Mm-hmm.
And overall, the sun, whatever is powering the sun from the center of our galaxy, Sagittarius A or B or whatever that is in there.
Yeah.
They call them black holes, but they're clearly not black holes. They're plasmoids. Whatever they are, that what we're looking at here is that variability. The
Yeah.
connection to the sun through the Birkeland current varies like this. And it's
Right.
some kind of background, non-periodic, this is, and then sometimes it flips.
Right. Right.
Sometimes it
Um,
flips.
the thing that I was struggling to say earlier, I think I have a better way of saying this now. So let's say during a reversal, like the I can never say that, Matayama.
Yeah.
You've got the overall polarity flip. So say, for example, before that, positive is in the south and negative is in the north. Well, really, all that's happening, right, is that you have more areas that are positively charged in the southern hemisphere than negative ones, making the South Pole positively charged, right? And obviously, when it flips, it's the reverse. You now have more areas of positive polarity in the northern hemisphere, making the overall dipole moment of the Earth, with positive at the north. But that doesn't mean that this area of the South, first of all, the South Atlantic anomaly, like I don't even know what the overall charge of that area is. It's just a weak spot in the magnetic field, right? That doesn't need to change in order for the overall polarity of Earth to flip.
Right. What's interesting also looking at this graph is it kind of is an anti-correlation with the Vostok data.
Mm.
If you look at the temperature data from the ice cores, we've got 100,000-year cycle that has no explanation, this ice age cycle.
Mm.
Take a look at this graph. From the Lechamp to the Blake, which are the two major magnetic excursions here, it's 100,000 years. And then to the Pringle Falls, it's 100,000 years. And it looks to be 100,000-year cycle here, not a 26,000-year cycle. And this may have something to do with what's driving the temperature here on Earth. But the Lechamp is 41,500 years ago. We didn't really start warming then. That was the coldest ever.
Right.
So low field strength, coldest on Earth, potentially.
Potentially.
Yeah, based on this graph. Very interesting. And look how deep the Jamaica Pringle Falls was. That was almost a reversal.
Yeah.
Because if the reversals only occur when the field strength gets almost to zero. And that last time that happened was right here.
Right.
700.
If you can imagine things like the field strength almost getting to zero, I always get this feeling of like there's like a bink, like something has to snap into place suddenly when the overall field gets low enough. Something that's interesting that came out of the paper that you mentioned earlier, the rapid changes in strength and direction of Earth's magnetic field over the past 100,000 years. One of the conclusions that they reach is that it's in the recovery phase of an excursion that the direction of the field happens, the change in the direction of the field happens the fastest. And I think that kind of reflects what we were just talking about, that kind of snapping back into place.
Yeah, well, look at this vertical line here at the bottom of the Brunus Mariama here, and then it goes vertical for like, this looks like for a few thousand years, straight the opposite direction.
Yeah, yeah. Yeah, so you can kind of see that in multiple places here where it's like on the way down, there's sometimes a sort of a stepping down, but on the way up, it's kind of, it's hard to tell at this resolution, to be honest, but.
Yeah, because like this one here, this looks faster down than up.
Right. Well, okay, but then.
This is the Lechamp is faster down than up.
I don't know if this really reflects the direction of the field, though. So, I don't know. Yeah.
Yeah.
I mean, there's so much to piece together here, right? It's like, if we want to try to connect this to climate, I think it gets really sticky because I think you could argue that the state of the magnetic field on Earth and how stable or unstable it is probably has an impact on weather.
Yeah.
And once you get to that
systems,
level,
definitely.
yeah. So once you get to that level, you have you have a lot of very localized variables impacting what's happening locally, which then could overall impact jet streams, etc. So I think it's going to be really hard to make that connection, because you're talking about measurements that are on a grand scale, and then you're trying to relate that to something on a much smaller level. I'm not saying that right either, but wow, that's pretty significant.
Well, and the change around 1970 something in the graph.
Yeah.
So
Wow.
there's very little data that you can find on Earth's field strength. They just hide it or something, or nobody's working on it. I just don't get it. So this is one of the papers, and I think it might be 18 years old or something at this point. And this is a graph in there. And we know since 2000 that the magnetic field has probably dropped an additional 10% or more, and could become more exponentially down than where it is from 1990 to 2000 here in this graph.
Yeah. I mean, the other thing I find really striking about this is just given the latitude, this is Massachusetts.
Yeah.
And that in 1900, that the field was 61,000 nanoteslas. That's as strong as the current strong areas are. That's as strong as the intense area in the southern hemisphere is.
Right. So you can extrapolate from that how much weaker the entire field is on Earth.
Right. I mean, unless this happened to be like a little hotspot in and of itself, but I don't even see that reflected. Can you go back to one of the global graphs of field strength from the last 11 years?
Where?
The ones we were showing in the beginning.
I don't know what you mean.
Oh, okay. Okay. Well, don't worry about it. Anyway, point being, that's clearly a very strong spot, even still today.
Yeah. So how significant is it? Well, let's take a look at this. We had a minor geomagnetic storm overnight for 3 hours. It got to KP5. And there was aurora in Maine.
Right.
That's insane.
Yeah.
So, but the bad news is that we're going into solar minimum for the next 4 or 5 years, and then we won't have much geomagnetic storming to reveal to us how vulnerable we are. It's going to be like 8 years from now, when we ramp up into the next cycle, that we may see how bad it is. You know, we may have G1 geomagnetic storms produce aurora at the equator in this next cycle.
Right. Well, and then also, when we're in solar minimum, that will also help contribute to a weakening magnetic field. You know, on a small scale, right? It'll come up again a little bit as we go back towards solar maximum again. But
yeah, and with our weak field going into solar minimum, if this may be the highest amount of cosmic rays, maybe the new modern maximum, it may also trigger a very large eruption, because VEI-7 eruptions occur on the cusps between solar cycles at the minimum.
Right.
That would be very bad for the world.
Yeah. I mean, it's a very interesting time to live. I mean, just the shift in the ability to see aurora at lower latitudes in the last even 5 years has changed pretty significantly. 5 to 10 years, I'll say.
Well, because we were in solar max, and it became apparent to us that we have a weak geomagnetic field. The weird thing is nobody's talking about it.
Right.
We've got all these new types of aurora, new colors, Steve, and aurora at the equator with geomagnetic storms has never happened before, and there's no one's questioning why.
Well, there are people that are questioning why, but they're coming up with like cockamamie theories about,
Climate
you know,
change. Yeah.
human induced, I don't know, weather modification. And I mean it's really, I mean there's a very clear like natural explanation for why we're seeing aurora at lower latitudes and different kinds of aurora. There's ample natural explanation for that. You don't have to assume that it's some kind of human induced manipulation. But I wish we were talking about it more, because it's very frustrating to see people assuming that it's something human induced. Where when you know the background science, you know that there's really no need for that explanation. You know, it's not,
Yeah.
this has happened before. The difference is we're now in a time where we're actually measuring the magnetic field, as well as monitoring the sun. And so we can really see the interplay of those interactions manifesting in our skies,
Yeah.
you know, whereas, you know, 1,000 years ago, we, you know, no, I don't think anybody was really offering a very good explanation for stuff like this.
So, in conclusion, I don't think the South Atlantic anomaly is anything other than an expression of the inner workings of Earth. That's it.
Mm-hmm.
It's just the way the Earth is designed. You're going to
Mm-hmm.
have high field strength and low field strength once you magnetize the planet.
Mm-hmm.
But it's change in size, I would think almost 100% is indicative of the weakening of our magnetic field.
Well, how could it not be?
Right.
Right? Because we have, I mean, we're looking at 3 areas of, you know, intense field strength. You know, one of them is weakening, one of them is strengthening, one is particularly strong. So if the overall magnetic field of Earth is weakening, then there must be a increasingly weak area that is growing.
Right.
Otherwise, we wouldn't. Otherwise, that calculation would not be correct.
And what else is happening here? This is becoming a very dangerous place to fly over.
Yeah.
The amount of, it's like flying into a microwave oven if you go over that dark zone.
Well, I think it's worse for satellites, simply because they're going to be, you know, closer to the edge of the atmosphere, and they're going to be receiving even more radiation.
Yeah. So, will this affect Starlink arrays? What does it mean for the future? As this continues to grow, this is going to be a significant problem.
Right. Well, and it's the fact that it is only one very weak area as well. Like, it has to get larger and larger, and that may be even more impractical for satellites, and because it's just harder to get around now, right? There might be an area on Earth where, for example, Starlink just can't go at some
Yeah.
point, right?
Can't work.
So if you're in South America here, you might be screwed as far as getting Starlink.
Right. And people might start getting cancer there. Any number of things can start happening.
You know, something else that I started wondering about today, I was thinking about the positioning of this weak field. And if we consider, like you just mentioned, that radiation would impact genetic mutation, well, does that have some relevance to the biological diversity, let's say, of the Amazon rainforest?
Yeah. And what's even more
No.
interesting is that when we're up in the high field strength, we will be able to witness in real time what is happening, what could be happening during the excursion, because it'll start happening over this weak zone.
Yeah.
Yeah.
Right.
Yeah.
Yeah,
That's
that's
interesting.
interesting. So maybe the smartest place to live would be like Australia, you know?
Or Siberia.
Right.
Yeah. The safest
Interesting.
place anyway.
Right. Right.
All right.
Hmm.
Great show.
Oh, but this, we have to consider this too. Let's say, like, during the excursion, what is it, the Lechamp
Yeah.
41,000 years ago, right? Like, I wonder, was there like a particularly weak spot over Europe? That seems unlikely given the latitude, actually. You know, I'm just thinking about the Neanderthal extinction. You know, that's something we would really have to like look at as far as like extinctions. Is there a relationship there to the actual geographical location of weak
Well,
areas?
when the field strength goes to zero, it doesn't matter where you
Right,
are on
right,
the
right,
world.
right, right, right,
It's all going to be a big purple.
right,
Yeah.
right. Yeah.
And that's why maybe Homo sapiens were in caves, Neanderthal was out on the steppe, and they were exposed to more radiation, and it didn't work out for them.
Right.
So much to consider.
Indeed.
All right, ladies and gentlemen, thanks for watching. We appreciate you coming, do all that Rumble stuff. Hit the thumbs up, share this with people you love, and be safe.
Bye.